It's still going to be recorded. It's just that I have to upload it at the end of a class instead of having it streamed automatically to YouTube. And also on top of that, the website is not going to work because, it's not hooking up to the website. But that's okay. I reviewed what we talked about in the previous class, and we're just going to continue with what we talked about from last Wednesday. So this class is one day behind the Tuesday, Thursday class. For those of you who want to, I want to know what's going to be in the next class, you can just watch the Tuesday, Thursday class because they're one class ahead of us. Okay, I think we'll catch up eventually because Thanksgiving is on a Thursday, so that won't impact us. And there are a few other holidays, too. So hopefully, this class is not at a continuous disadvantage when it comes to time. All right, so we're getting back to base conversion. Okay, last time, I reviewed my own YouTube, and I, found that we talked about binary conversion last time. So what we'll do today is to come up with some equations so that we can convert to any base. So you just tell me what the value is, which is the quantity. You tell me what base you want to convert to, and I'll give you a closed form equation to do it. Okay? And without internet connection, I'm just going to use my electronic whiteboard. I'll keep trying, just in case it comes back, and that'll be handy, but I'm not counting on it. All right, so what we'll do is we are going to use Zerno for the most part today. It's just kind of my electronic whiteboard, so this way you don't have to write anything down as long as it is on the projector. And you might want to remind me to upload everything onto YouTube afterwards. Well, as soon as I get network connection back. All right, so let's go ahead and get started here. All right, so the first thing we want to do is to do base conversion. And instead of doing a base conversion to some base that we are not familiar with, we'll do base conversion to base 10. Okay, doesn't sound very exciting, does it? Okay, base conversion to base 10, something that we already know. But it will illustrate the process, or the mathematical concepts that we need in order to do that conversion. So we'll start with this. And I'm going to start with a number. Let's say this number is 1,736. Okay, that's the number that I want to. This is a base 10 number that specifies the quantity that I want to convert to base 10. Now, I understand that sounds really kind of not so smart, okay? But that's what we'll do, okay? So to be more specific, I want to isolate the digit 7. I want to isolate this particular digit. This is digit 0, okay? D0. This is digit 1. This is digit 2. And this is digit 3. So in terms of nomenclature, this is how I would name the digits. Now this particular way of naming digits is not only specific to base 10 number. I can apply the same thing to any base. It really is just saying which one is digit 0. Well, as it turns out, this 6 is digit 0 because it tells me the quantity of 10 to the power of 0. That's why it's called digit 0. So remember, we count from 0 when we count digits. All right, so with that, explained, the question now is how do I get that 7 out of this entire number? In other words, what kind of expression do I use so that 1,736 as a quantity is a parameter to that function, but what it returns is really just 7 all by itself, okay? So the first thing we might want to do is to say, well, the 36, the 3 and the 6 are not needed. So how do we get rid of the 3, 6 out of 1,736? What do you think of dividing this number by 100? Let's see what that's going to do to us, okay? So 1,736 divided by 100, which is 10 to the power of 2, right? So we'll rewrite this as 10 to the power of 2, and that's going to give us 17.36. Is that okay? No big surprises here. So now the question is, how do I just get rid of the fractional part of a value? What function do I use to get rid of it? It's called the floor function. Okay, the floor function can do this. So I'll first present what it looks like, okay, and then we'll talk about what it means. The floor function symbol is kind of like a square bracket, but without the top portion. So this is the floor function symbol, like so, and it returns 17 in this case. So I'll explain what this is the floor of x, which is the largest integer that is less than or equal to x. So excuse my laziness, I just do not want to spell out the entire less than or equal to, so I'm using the symbol to represent less than or equal to. Yes?
Could we use the modulus operator?
The modulus operator does not work on fractional parts.
I mean, just for the 1736?
No, because if you use the mod operator, you get the 6 back, right? If you mod 10, you get the 6 back. If you mod 100, you get 36 back. If you mod 1,000, you get 726 back. You're not quite getting just the 7 because it's not the least significant digit. Now, if the 7 is the least significant digit, yes, you can just mod it.
Gotcha.
Okay. So in this case, are we okay so far with this process? I want to extract D2 out of this particular quantity. And the first thing we do is to divide it by 10 to the power of 2, because the idea is I want to get rid of all the less significant digits, get the floor to get rid of all the fractional part of 17.36. Is that okay? Is that okay? So far? Okay. So now I have 17, which is close to what I want, but not quite. Now we use the mod. Now we use the mod. So now we say, I don't need the whole 17, I just need the 7. Forget about the 1 or any other more significant digits. And mod can do it, because mod is the remainder of a division. So when you say 17 mod 10, I really hope that you have been introduced to the concept of modulus or remainder operation in C and C++, because this is one of the more, it's as useful as division itself, okay? Except it does not return the quotient, it returns the remainder of a division, okay? So the remainder of 17 divided by 10 is just 7. We got our digit, okay? So let's revisit the whole process, okay? Let's rewrite the entire thing in one single expression and see how we did this. So what we did was we first divide the value that we have by 10 to the power of 2, and then we take the floor of that, and then we mod it with 10. That is how we got to the digit 7. Okay, so I'll just write the equal to 7 here, which to emphasize that this is how we did it. Do we have any questions about this very concrete example of extracting one digit out of a quantity, out of the base 10 representation of a quantity? Are we doing okay so far with this? Good, okay. So next, I'm going to generalize this, okay? So I'm going to generalize this while keeping the expression in view. I'm going to ask you a different question, okay? So I'm going to say, what if we want, oops, okay, I do have undo. What if we want digit k in base b of quantity or value? You can choose which one you want to use, v. This is the question. In other words, instead of 1736 as a value, okay, instead of base 10, instead of digit 2, we have digit k. I'm parameterizing everything that I possibly can parameterize in the process. Is that okay? So how would that expression look like to extract that digit k in base b of a quantity v? You just take a look at what we have and say, oh, 1736 is v. 10 is our base. 2 is our k because we are extracting digit 2. Is that okay? Do we see how I'm doing all the substitutions? I'm going to show you graphically. Okay, this is kind of slightly green. This is our v. This part here is our b, which represents the base. This one here is our k, which is telling us which digit we want to extract out of that number. And guess what? This one here is b again. Are we doing okay so far? Because I'm just trying to show you how I came up with this expression, which is what I'll present next. It's in the notes, okay? So if you have read ahead of me, you would have seen it already. But this is, I did not explain how I came up with that expression. This is how I came up with that expression. Is that okay? So are we ready for the final form of that expression? The general expression? It just looks like this. It looks like this, okay? V, which is the value, divided by b, which is the base that you want to express the value in, to the power of k. K is representing which digit we want to extract. And then once you take the floor function of the division of the result of the division, you just have to mod it. Okay, you can write mod mod, or you can use the percent symbol. It's up to you. B, that's it. This is dk in base b to as a part of a number to represent v. Now, this also, is very important, for us to differentiate what is a quantity or value. I consider those two pretty much the same, versus a number. Okay, we talked about that in the previous class already. Conceptually, those are different things, even though when we think about it, they seem to be synonymous. Okay, maybe they're synonymous in some other scenarios, like if you talk to an English professor, okay, and you ask the English professor, is there a difference between a value versus a number? That professor may say, no, I don't see any difference, okay? Because in an English class, there's no need to differentiate between those two concepts. But in this class, there's a huge difference between those two concepts, okay? The quantity is really just something that you want to represent, okay? Last time I drew some dots on the whiteboard, and that is representing the quantity I want to represent. A number is how you communicate with somebody else or a computer what quantity we are talking about. So the same quantity can have an infinite number of representations, and the number is just one representation. Is that okay? If you still want to kind of think about how those are different, you can just think about a change, in money amount, a change of $27.35. Okay, how you make change for that amount? Well, you can have 2,700 something pennies. That's one representation. You can have one $20 bill, one $5 bill, two $1 bills, and so on. That's another representation. That is what we are talking about. You can even convert that worth, okay, into a foreign currency. You can convert it into Japanese yen if you want to. It can still represent worth, even though the unit has changed and the representation has changed. Is that okay? All right. I'm not sure whether I went through this with this class, but if you have, okay, so given a number in base b where di is digit I of the number. The value, you don't have to write this because it's all in the notes. This part is definitely in the notes. The value represented, I'm going to call this V, is the following. So V is the summation of I going from some number, I'm not going to use a negative infinity here, but I'm going to use a symbol. Okay, we can use L to M di times b to the power of I. Okay. Did I present something like this in the previous class? Did I talk about the sigma notation? Nope. Okay, but that's fine. The sigma notation is called the summation, operator, or the summation symbol. And what we have here is a loop. Okay. So let me just kind of talk about the summation summation operation first. Okay. So we'll get back to this, but I'm going to open a new page first and talk about the summation operation first. Okay. So we'll take a look at this thing here. Okay. Sigma. You always have some kind of an index to tell you which quote unquote iteration you're talking about, or which term you're talking about. We'll have a start, and I'm going to use the same symbol here. So we'll have an L here and an M over here. But instead of having a particular expression here, I'm just going to say it is some kind of function applied to I. This is the notation. And I want to explain what this notation is doing using a C function. Is that okay? Now, for the most part, for this class, we are concerned about mostly just integers. But since we may not be dealing with just integers, I'm going to convert to a type of value, okay, which can be integer, which can be just a real number. Okay. So the function in C would look like this. It returns a value, and I'll call this function name is sigma. And it's going to take 1, 2, 3. It will take 3 parameters. So the first parameter is L. L is definitely an integer. The second parameter is M, which is also just an integer. The third parameter is a pointer to a function. How many people have exposure to a pointer to a function from cisp 360? So I see about half the class having exposure to that idea. Okay. So the idea of a pointer to a function is so that you can pass a pointer as a parameter into a different function, or possibly the same function, so that you can parameterize it. Typically, they talk about that in quicksort. A prime example of using a pointer to a function is a qsort or quicksort. But if you have not been exposed to that concept, it's okay. We can kind of go over that just a little bit here. The way you express a pointer to a function as a parameter is you have to specify the return type, and then you use this kind of little. It makes sense, but it makes sense eventually. But this is how we specify a pointer to a function. You can see how we use the symbol asterisk, right? Because in general, when you use the asterisk, it means it is a pointer of some kind. But in this case, it's a pointer to a function. But you can say, well, but this means it is a pointer, f is a pointer to a value, not a function. You're absolutely correct. I'm not quite done with the notation yet. So what you need to do next is to specify the actual parameters of the function pointed to by f. Okay, is that okay? All right. So that is going to be of integer type, and we'll call that x. Okay, how you call the name, this part here is not important. Okay, so this is the prototype of sigma, and the rest is what we do with it. We have a local variable integer I, and then we have a for loop. The for loop is actually quite simple. we start with the value L, okay, the lower bound, and then we stay in the loop as long as I is less than or equal to M. M is the maximum or the upper bound. And for each iteration, as a post operation, we increment I to get to the next iteration. Is that okay? And I'm forgetting one local variable as well. So I'm forgetting a variable of the type value. We'll call that sum. And it is initialized to 0. I probably should initialize it as the first part of the for loop, but since I didn't leave enough space to do it, I'm just going to do the initialization out of the for loop. And then for each iteration of the for loop, this is what we do. Sum plus equal to f of I. And then when the loop is done, all we do is to say return sum, and that's it. All right. So do we have any questions about the function itself? Forget about the sigma notation in mathematical notation. Do we have any question about the sigma function? It is passed 3 parameters. L is the lower bound, M is the upper bound or the maximum, and then F is a pointer to a function. And for that particular function, you have to give it a particular integer as an argument, and it returns a particular value. And then what sigma itself as a function does is it just has a loop. The loop is just going through all the values from L to M inclusively. Okay? And then for each value between L and M, okay, it's going to evaluate the function f. Whatever f is returning, you add it to a running sum, and when you're done with this entire loop, you return the value sum, and that's it. Do we have any questions about this part? Yes?
Value and data type?
Yeah, value is basically data type. If you really want to make it concrete, you can say double or float. Okay.
Sigma is the name of the function.
Sigma it's a pointer to a function. So we can parameterize it. We can pass any function to this name, and it will still be able to perform the summation.
Oh, I didn't see the comment. It's like a continuation of the line below sigma, right?
Which
Where it
line?
says value, parenthesis, asterisk, f, parenthesis.
Uh-huh.
Yeah, like that. I was just,
You mean this part here?
yeah, it's a continuation of the top.
Yes, it is. It is. F is the third parameter. Yep, you're correct. So are we okay with this? Yes.
So it doesn't really matter what function is happening. We're just concerned about summing up
Yes.
return value.
Yep.
Okay.
Yep. Yeah. People with some exposure to pre-calc, probably have encountered this concept already. If you're taking calculus, it's just a continuous version of summation. Yep. Huh?
What's the third parameter
You mean parameter f?
for? Yeah.
Okay. So this is how we define sigma. Is that okay? Okay. So connecting back to what we are doing. Okay. So connecting back to what we are doing, we're going to define another function. Okay. So we'll say value. We'll call this, VD, value of a particular digit, and shucks, it takes more than one parameter in this case. Okay, but that's okay. I'm just gonna kludge it, at this point. Okay. So VD is going to represent something like this, okay? So it's going to be DI times B to the power of I, okay? But since I only have one single parameter, the other two have to be quote-unquote global variables, but just kind of consider those as global variables, okay? So this is going to return, D is going to be an array, okay? So we're extracting the ith digit in a number, and then B is to the raised to the power of I. So we have, I think it's just power or power. I cannot remember the name of the power function, but you have base b raised to the power of I. Is that okay? So yes, this is bad programming practice because in this case, the only way for d and b to get into the function is they have to be global variables. There's no other way to get these. But just assuming that d and b are both global, are we okay with vd as a function? Okay. So now we can go back to the original equation. So v is basically applying sigma as a c function. We specify L as the lower bound, what is our least significant digit, M, which is what is the most significant digit, and then what we do is we pass VD as the third parameter, or the address of VD as the third parameter. In other words, VD is going to be corresponding to parameter F when we define sigma. Is that okay? Is that sufficiently explaining what sigma does? Okay. Or I can also use another way to illustrate it, which is probably a little bit easier, okay, is to use it an example. Okay, so sigma I equals 2 to 8. Don't ask me why it is 2 and 8, it's just an example. And if I want to add, I squared as each term, so this becomes 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared plus 8 squared. That's probably easier to explain it. Yes? Okay. So, given this is kind of, what we are dealing with, and switch back to this page, let's focus on this one now. What does that mean? Well, let's put some concrete values to this and figure out what it actually means. The first thing is I'm going to use base 10 because we are all familiar with base 10 already. So we'll say, well, let's assume b is 10 because we're dealing with base 10. And then we'll assume L is -2 and then M is just 2. And then we'll have, all the D's, right? So D -2 is 5, D -1 is 2, D0, I'll give it a 4. D1 is going to be a 0, and then D2 is going to be a 1. Okay. So all of these things here, they're really here just to give you an example. Okay. So I'm basically saying, for instance, okay, assuming we're dealing with base 10, the least significant digit is 2 places to the right-hand side of the decimal point. The most significant digit is 2 places to the left of the decimal point. And the individual digits are 1, 0, 4, and then the decimal point, and then 2, 5. Now the question is, what value is it representing? Is that okay? So we plug in all of this into this equation, and then we try to figure out what V is. What do you think V is? It's going to be 104.25, right? Because, if you plug in everything, what is V? V is now D2 times 10 to the power of 2 plus D1 times 10 to the power of 1 plus blah, 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 D -2 times 10 to the power of -2. I'm just writing out the sigma, right? D2 is 1, 10 to the power of 2 is 100. So we have 100 plus 0 because D1 is a 0. D0 is a 4, and that's multiplied by 10 to the power of 0, which is 1. And then we have a 0.2, and then we have a 0.05. Is that okay? That's just, 104. Okay. So are we good at this point? All right. Well, let me ask you another question. Can I come up with exactly the same value, but I change my base to 2, for instance, and then I'll let you guys figure out what is the least significant digit, what is the most significant digit, and what the digits would look like. In other words, I'm asking you to do base conversion. Is that okay?
With the same number.
With the same value. So I want everything to add up to just 104.25, but I'm changing the b to a 2. So let me just let me mark this up exactly how I want to do it, and then we'll figure out how to do it. Okay. So the big change is I'm going to start with this and say, okay, let's not do base 10, let's do base 2. All right. So when you do base 2, then the m and l, they probably have to change. Well, actually, in this case, l is okay to be -2, but m has to change. Okay. So I'm just going to say, we'll change m. It's okay to make it more than what it needs to be. Okay. Because we just say, okay, we don't need to use all the digits. So I'm just going to change this to just a tad more than what it needs to be, which is 7. Are we good? So now the question is, assuming that this is what we're changing it, what is going to be D7? What is going to be D6? What's going to be D5, D4, D3, D2, D1, D0. And then scroll a little bit. We have D-1 and D-2. Okay, so that's the question. Yes?
How do you know what the least significant digit and the most significant digit will be before you do the conversion? Are you just kind of guessing?
I'm not guessing. I'm actually looking at the value that I need to represent. And a quarter is 2 to the power of -2. That's how I know that L is -2. And then I look at 104, it is less than or equal to 128. 128 is 2 to the power of 7. So I know if I make M 7, it's more than what I need. Yep. So that's just because I have the experience of looking at a value and can identify, what I need in terms of the range of digits base to represent it.
What if it was some weird base that you're not familiar with? Don't you need to know these variables before you start?
M would still be easier is the easy one to figure out. Like if M is, if B is 7, which is base 7 numbers, I look at this particular value and go like, the largest power of 7 I need is 49. Because, 349 is already more than this 104. So I would not only need 2 digits in that case. So M can remain as 2 if I change the base B to be 7.
So you're doing some arithmetic beforehand to figure that out.
Correct, yes. So in my head, I'm already doing some quick calculation to figure out what range of digits we're going to need. Yep. But assuming we already know how many digits we need to each side of the decimal point, now the question is to figure out, okay, what should be D7? Well, D7 in this case is going to be multiplied to 2 to the power of 7. 2 to the power of 7 is 128. Do we need 128 to represent 104 and something? The answer is no. Okay? So you say, nope, do not need one of those. So D7 is a 0. Next, do we need a 64? Yep. Okay. Once you take care of the 64, you have 40. You have 40. Exactly 40, right? 40.25. So in 40.25, do we have a 2 to the power of 5?
Yes.
Yes, because that's a 32. So you say, yep, we need one of those 2 to the power of 5. So that's 32. So we got, 8 point something left, right? 8.25. So do we need any 2 to the power 4? Nope. Do we need any 2 to the power 3? Yep. So now we take out the 8. Okay, we only get 0.25 left, right? Do we need any 2 to the power of 2? Any 2 to the power of 1? Any 2 to the power of 0? Any 2 to the power of negative 1? That's a half, right? That's a 0.5. Don't need any one of those. Do we need any 2 to the power of negative 2, which is a quarter? Yes, we need one of those. So now we go back and figure out all the individual d's. So now, when you apply the blue stuff to this sigma notation, what v are you going to get? The same as before, right? Because all we did was to change from a base 10 representation of the same value. Now we convert to a base 2 representation, but of the same value. Is that okay? So I understand the symbolism makes it kind of harder to understand because I'm throwing in all kinds of math stuff, right? Sigma is new to some people. I'm abstracting the digits into just d subscript I. I'm abstracting the base to b, and I'm abstracting the position of the digit to I inside the loop here. But this allows me to have one single equation to say, this is how we do things regardless of the base. Is that okay? All right. And abstraction is a big thing in computer science. Okay, you might think, well, but programming does not involve math. It does not involve abstraction. It involves abstraction. Every time you try to come up with an algorithm to do something, you are abstracting an operation. You do it by hand a few times, okay? That's a concrete example. Then you go like, okay, but how do I describe this in an abstract way so that the same description can be used over and over again to process the individual problem instances of this type? That is abstraction. Well, since we're talking about abstraction, how many people have this experience of you're working on a homework assignment in 360 or 400, or 430, okay? It doesn't matter what class. You're working on a program and you realize, oh, I have some code to do just that. I'm going to copy and paste it. And before long, you realize, oh, I have copied and pasted, the same chunk of code many, many times over my program. I have that experience all the time, okay? Because I'm lazy, okay? So when I say, oh, I need to do this, wait, the program has some other code earlier that is doing this already. I just go to that place, copy, paste, change the references of the variable name so that it is correct in the local sense, and I'm done. But what is a better way to do it? Instead of copying and pasting the code, what is a better way to do this? Turning it into a function. Yeah, turning that common piece of code into a function, so that I can call the same function from different places is a better way to do it, right? Why is that a better way to do it? Okay, space. Fewer lines of code. But there's more than that. Less room for error, exactly. Now, whether I copy and paste or to turn something into a subroutine, I'm still the stupid me who makes all kinds of mistakes. If I copy and paste, I'm replicating that mistake all over the place. In other words, later on, if I found that, oh man, I should have used a less than or equal to, not just less than, now I have to go back in time and say, how many times have I copied and pasted that code? And I have to fix every single one copy of those, because otherwise the program would be wrong. And there's no easy tool to help me to do it. On the other hand, if I turn it into a subroutine first, and I call the same subroutine from different places, I'm still the same stupid me making that same stupid mistake. But I only made that mistake once. If I fix that one subroutine, I'm fixing everything. I don't have to fix the calls themselves. I just fix the definition of the subroutine. Is that okay? But guess what? That is abstraction. You're looking at something that is concrete, and there are several copies of that, and you're saying, Well, I can see there's a lot of similarity between this kind of code. Can I turn it into just one single copy? That is abstraction. So what I'm doing here is, once again, abstraction. What I did way earlier in today's lecture is also abstraction. Let me just kind of scroll back to show you what I mean by that. This is abstraction. I start off with a very concrete values, 1,736, and I said I just want the 7 back. This is concrete, okay? Nobody can argue, this operation will get me the 7. But once I have this concrete example, I turn it into one single expression, and then I ask, given this, can I make it generalized? Yes, V goes here, B goes here and here, K goes here. Now I have a generalized equation or expression to get me a digit in a particular base, when I need a number to represent a particular value. Is that okay? Because I don't just want to present what the material of the class. I also want to kind of show you guys how I come up with that material. Is that okay? All right. Because if you guys can learn not the knowledge, but how I come up with the material of this class, then you have just equipped yourself to learn on the fly, on the job, any programming language, any programming technique that you need, which is great because I will no longer be needed. With almost every single job that I took on, my usual way of operating is to try to work myself out of that job so that I am no longer needed in that job. All right, so are we good so far? Okay. So once we understand, how to convert to a particular base and how to convert from a number representation and get back the value being represented, the next question is, well, how do we add and subtract? Okay, we'll focus on one at a time, how to add. Okay, are we good so far? So we're making a transition. This is actually moving on to another module in the notes. I'm just going to double check and see if my internet connection is back. Yep, it is back. Okay, cool. So this means I can at least get back to Canvas and show you where we are in terms of the notes. This is the other class. And we are on the Monday, Wednesday class. So we are basically done with this module. The values, numbers, and basis module is done. I talked about all the concepts. The equations and expressions, they're all in here already. Okay, so there's no need to massively copy stuff. We're now moving to binary number addition. Okay, so I'm moving ahead, which also means your reading assignment for this week is to at least catch up with this and possibly finish this entire thing. Before Wednesday, you might want to read the entire edition. There will be something you don't understand. That's fine. We'll go over all of that stuff in class. But at least read through it so that you have an idea of what we will be talking about. So now we move. Yes, go ahead.
I noticed that at the end of the reading, it says exercise, and you'll suggest that we write a program. Is
Yep.
this the stuff that is not graded that you were talking about earlier?
That's part of what is not going to be graded. Okay. So that's good. Okay, so at least one person is reading the notes. Because at the end of a module, sometimes I will give you a suggested activity. So in this case, I'm asking you to use any language to write a program to do base conversion. So you can type in a base 10 number, and it will convert it to base 6, base 7, base 5, or whatever weird base you choose to use. Or it can be the other way around. Okay, you can have it to input a particular number in a particular strange base, and then it will print out the base 10 representation of that value. Okay, So that would be a good exercise to do because by writing that program, you're tying in the concepts that you have learned in class, and it helps to solidify your understanding of the concepts involved in that module. But it's not something you have to turn in, so I wouldn't do it if you do not have time to do it. Like if you're taking too many units and you're already fully loaded, you can just go like, okay, I'll go through the mental exercise, but you don't have to spend the time to actually struggle with a program, like the compiler and the syntax errors and stuff like that. But going through that mental exercise can still be helpful. All right, so any other questions related to base conversion and concepts related to base conversion? No questions. All right. I noticed that I always forget to pass the row sheet, but this time I remember. There you go. And so what we'll do now is to move on and talk about addition. Okay, so it's a very simple concept. You guys have been doing it for many years, but I'm going to talk about it anyway. Okay, and we'll start with something that you're familiar. Well, hopefully familiar. So we'll start with base 10 addition. And we'll start with something that seems pretty easy. This is all in base 10, okay? 6 plus 8 in base 10. What is the answer? You can call it 14. You can call it 4 with a carry of 1, okay? So you can say it's 4 with a carry of 1. I did not see anyone, using a piece of paper to work this out. I did not see anyone using a calculator to work this out. And I did not see anyone chatting with a neighbor to say, so what is the answer? What is 6 plus 8? I did not see any. Doesn't mean that it did not happen, but I'm suspecting it did not happen. So how did you know? How did you know the answer of 6 plus 8 so quickly? It's memorization. Exactly. You have memorized all of this already. If I ask, what is 8 plus 9, you go like 17 or 7 with a carry of 1. You know it almost instantly because you have already memorized the whole thing, which is good and bad in different ways. Okay, it's good because you are familiar with addition. I don't have to send you to remedial math. Okay, that's the good news. The bad news is, if I ask you about a concept, you may not remember the concept. What is the meaning of a carry? Okay. It's kind of like an overflow, because what is the range of value that a single digit can represent in base 10? It's up to 0 to 9. Very good. Okay, because I asked for a range. So the range is going from 0 to 9. The quantity 10 itself can no longer be represented using a single digit. And that's why we write it out as 1, 0. Because we have the 0 means, in terms of unit, that's not sufficient. But we have 1, 10. Okay, that's what the 1 is representing. Is that okay? How long did it take you to memorize, all the addition rules in base 10? And how did you learn those rules? What tool did you use to learn those rules? Repetition, okay, but did anyone use blocks, when you were in elementary school? I remember vaguely using blocks, and I still remember the block representing a length of 2 was pink. Don't ask me why, but that just kind of stood out in my memory. Okay, so you don't have to write this down, but if you want to, that's fine too. So when I ask you what is, let's say 2 plus 9, okay, you can just draw a block of 2, okay, and then you draw a block that is of length 9, okay, so it's 4 on one side and 5 on the other side. Okay, so this is one physical block. This is another physical block. Then when I ask you how do we represent it as a base 10 result, then what you do is you put these blocks on a piece of paper that has a marking clearly indicating what is 10, right? So when the length of the 2 blocks, added up is exceeding the length of 10 blocks, then you know that we have a carry of 1, and then the result is whatever is left over here, which is also 1. Sometimes you call this 11, other times you call this, it's 1 with a carry of 1. But that's how we learn. That's how we visualize and understand the concept of carry. Okay? And in base 10, in elementary school, it's not something simple. Okay? Most kids will probably need a week or two, to master, the addition, rules. Is that okay? Are we good? So which part of this picture do you think has to do with the base? It's base 10, base 2, base 7. Which part do you think is based on the base? Yep, so you're both correct. The width of this part is specifying the base. Okay, is that okay? All right. And what about, what blocks can I play with? I can have a block of 1, I can have a block of 2, I can have a block of 3, blah, 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 blah. And what is the longest block I should play with when I'm trying to learn addition in base 10? A block of 9, right? Okay, so this is the longest block I should play with when I'm learning base 10. Is that okay? Because each one of these is representing the value of 1 digit, but we can only go up to 9 in base 10. And to understand the concept of a carry, we need to have a marking of 10, because that is when we say, oh, we cannot use a single digit to represent a quantity anymore. We need to use at least 2 digits to do it. Is that okay? Okay. What about base 2? So if I just roll back in time and I say, forget about base 10, that's a stupid base to learn, and let's learn base 2 from the get-go. What do you think would change about this picture?
Blocks of 1.
You only have blocks of 1, exactly, because you cannot have a block of 0, so you only end up with a block of 1. Okay, so I'm going to use green to represent that, okay? You don't have to write this down. I really don't think you have to write it down. Oh, this is actually 1 to 9, not 0. 1, 2, 3, cross that out. But you only have 1 block, because a block of a length of 2 is no longer relevant, because a single digit in base 2 can only represent 0 or 1. Okay. What about on this side? That's it. You measure against a width of 2. Anything that is 2 or more needs at least 2 digits. Is that okay? All right. So now we just kind of write down here and go like, in base 2, what rules do we have to learn? So we are now talking about base 2. Okay. What do you think is the result of this addition in base 2? I have nothing to begin with, and someone gave me nothing. So how much do I have? Are you really sure we are talking about base 2?
I'm gonna go out on a limb.
Regardless of the base, because nothing is not base dependent. Okay? All right. So I think we can say that 0 in base 2 plus 0 in base 2 is 0 in base 2. Okay. What about 1 plus 0 in base 2? It's just 1. Okay, very good. 0 in base 2 plus 1 in base 2
You get 1.
is just 1 in base 2. Okay. The only one that is tricky is 1 in base 2 plus 1 in base 2. It is not 2 in base 2, because remember, in 2, you only got 2 digits. You only got 0 and 1 for each digit. So how do we represent the quantity of 2?
1, 0.
1, 0. Very good, because we need a carry. Okay? So the result is a 0, but it has a carry of 1. So with the other 3, I can say, well, instead of saying there's no carry, we can say they all have a carry of 0. Is that okay? We don't usually do that in a normal long addition, but in this case, I want to emphasize we do want to know what the carry is. It's just that sometimes, most of the time, the carry is a 0, and we only have one case where the carry is a 1. Are we okay with this picture? Yeah? Okay. So now, instead of looking at this picture in this way, I'm going to use a table. Because a lot of times, once you turn something into a table, you will recognize patterns better than looking at individual cases like that. So I would just say, we have x, we have y, and if you really want to know what x is the first number to be added, and y is the second number to be added. Okay? So I just give them labels. So we now want to work out what is 0 plus 0, what is 0 plus 1, what is 1 plus 0, and what is 1 plus 1. Are we good? Just nomenclature. And we also want to designate the result of a calculation. So these are results of an addition. I'll call that R. So I'm just going to link all of these to R. Is that okay? So I'm going to use a R column in a table. So 0 plus 0 has a result of 0, 0 plus 1 has a result of 1, 1 plus 0 has a result of 1, and then 1 plus 1 has a result of 0. Are we okay with this? I'm just moving stuff around and into a table format. So the last portion is the carry. Okay, so I'm going to say, okay, this thing here, this thing here, this thing here, and this thing here, that's my carry. Okay, so I just say, okay, these are all just the carry. And in the table, I have another column to represent the carry. 0 plus 0 has a carry of 0. 0 plus 1 has a carry of 0. 1 plus 0 has a carry of 0. And 1 plus 1 has a carry of 1. Are we okay with this table? X and Y are quote-unquote the inputs. R and C are quote-unquote the output. So X and Y are, each one is representing a digit in base 2 addition. R is representing the result of the addition, and then C is representing the carry of that addition. Is that okay? Great. Well, this is very encouraging because I'm looking at zeros and ones. Feel comfortable because when I see something only as zeros and ones, I say, oh, so I can use physical quantities that we talked about from day 1 in this whole semester to represent all of this stuff. I can say a 1 is a voltage above a certain threshold, a 0 is a voltage below a certain threshold, or I can say a 1 is a transistor turned on, a 0 is a transistor turned off, and stuff like that, because it's binary. Okay? But then I go like, unfortunately, these are arithmetic concepts. Addition is not a Boolean concept. It is not about true or false. It is about values, right? I have 1. Somebody gave me 1 more. Now I have this much. Okay? That is an arithmetic concept, not a Boolean concept. Go like, but transistors cannot do that. Okay? We have these fancy, gates, starting with an AND gate, and then we can make a NOT gate, we can make an OR gate, we can make an AND gate, but none of those gates understand addition. Okay? So now we have a little bit of a problem, because how do we do addition in transistors? Because that's the ultimate objective. All right, so we'll do the easy one first. Okay? We'll take a look at C. I'm just isolating this table just so that we can focus on C. There's no new information here. It's just isolating one column out, so it becomes more obvious. Does it seem to you that even though carrying is an arithmetic concept, we might be able to use a very simple Boolean operator to do exactly the same thing? Does it look like there's a Boolean operation that can give us the same result? And D, just a regular conjunction can do it, right? So that's good. I mean, that's nice because I can now say the carry of adding x as a bit and y as a bit is really just x logical and y. I feel really good about this because I know how to make an AND gate. An AND gate can be made out of several NAND gates, and I know how to make a NAND gate using 2P and 2 N transistors. So I feel grounded. I feel that I can make connections all the way back to devices that I can actually purchase and make things out of it. Is that okay? So now we look at R, okay? And we say, that doesn't look too simple. Okay, because 0 plus 1, 0 plus 0 is a 0. 0 plus 1 is a 1. 1 plus 0 is a 1. But 1 plus 1 has a result of 0, even though it has a carry of 1. I go like, well, we almost have it because, or, if I just change this to a 1, we would have OR, logical OR would do it. But it's not quite doing that, right? There is actually a logical, not logical, bitwise operator in C that can do exactly that. It's called exclusive OR. It looks like a caret. It is the caret symbol in C and C++, but most classes don't talk about it because it is a bitwise operator. So let's just say that we cannot use exclusive OR as a logical operator because we have not been exposed to that concept, okay? So now the question is, well, is there a longhand and complicated way to express R, but only using Boolean operators? That becomes my next question is, well, if I cannot find a single operator to do it, can I use an expression using only Boolean operations so that I can have R? What do you think? So instead of deriving that, I'm just going to give you the answer, okay? So what if I say, R of xy, the result of adding x and y as bits? What if I say, let's go ahead and do this? Is x logical and not y, or not x logical and y, not negated? What do you think? Well, all we have to do is to evaluate this proposed expression for each row of the truth table. If we get back what we need, then we can say, yes, it gets the job done. It looks kind of clumsy, but it gets the job done. Okay? So let's do it. Okay? So you guys can do it with me. The first row, x is false, y is false. Okay? Plug in those values. If x is false, the whole conjunction has to be false. If y is false, this also has to be false. So we end up with false or false, which is false. Okay, so far so good. Next row, x is false, y is true. X is false, same as last time, so x and not y is going to be false. But this time, y is true. So if y is true, then this is true. But since x is false, not false is also true. So on the right-hand side, we got true and true, which is true, right? And now we have false or true, so the entire expression is true. Very good. The next row is a mirror image of the previous row, so I hope you're fairly convinced that it will give you an answer of true. Okay, because it's kind of symmetric, we just kind of flip the x and the y. It works because conjunction and disjunction are both commutative operators. Okay? What is a commutative operator? What does it mean? Order does not matter. Okay? You can switch between the right hand side and the left side to the same result. Okay? Very good. So we are only concerned about the last one now. Okay? The last one says, x is true and y is also true. So what's going to happen to this expression? Well, it doesn't matter which way you're looking at it because each conjunction has a negation of either x or y, right? So if both x and y are true, then one of the negations is going to be, the negations would be false. So you end up with false or false, which gives us false. And that's why we can now say, oh, now we have just figured out a way to express the result of adding 2 bits. Even though it inherently is an arithmetic concept, is a counting concept, we can implement it using only Boolean operators. Is that okay? Is that cool?
Yeah.
Because now we can do arithmetic operations, but only using Boolean operations. We have bridged those two concepts. That I think it's really cool. So before I go any further, I'm just going to say, what other way I'm going to use to represent this. If you're going to electrical engineering or computer engineering, these are very clumsy notations. They're long, they take up a lot of space, and they're not intuitive. Okay, so there are other ways to express the same thing. In logic, a lot of times people use multiplication to represent conjunction because when you look at abstract algebra, it does have a lot of properties of multiplication. So we say, oh, we just use multiplication, and we don't even bother to use the dot, in this case. And negation, in this class, I will still use an exclamation point to indicate negation. But negation can also be represented in electrical engineering or computer engineering with an overbar. So if you see an overbar over something, it means logical negation. But in this class, because an exclamation point is much easier to type, I'm just going to use an exclamation point. Okay. And we'll still use parentheses, not x and y. And then disjunction shares a lot of common attributes with normal addition. So this is not an arithmetic addition. I'm simply borrowing the addition symbol to mean disjunction in a Boolean expression. So I just want to make it extra clear. I'm just borrowing representations from arithmetics, but these are all Boolean operations. But this makes it a whole lot easier to type. So are we okay so far with this? So I have just talked about the basic idea of base 2 addition. Do you think elementary school students will thank me if I go to their elementary schools and say, let's not do base 10, let's do base 2 from here on? Before they get exposed to base 10, I think they will like it. You guys don't like it because you have been poisoned by base 10 already. So now you need to go through a long detox, process to get base 10 out of your head. That's why you don't feel comfortable with base 10. Now base 16 is nice, okay, because there's a very easy way to convert from base 2 to base 16. Now since you asked that question, I'll answer that question right now, but we'll revisit that question also throughout this class. So let's talk about base 2 to base 16. Okay, I'll give you a pretty long string of I got that already, and that. Okay. The problem with base 2 is you need a lot of digits to represent the same quantity. Okay. So if you think about 32 bits, okay, 32 individual base 2 digits, it can only represent up to 4 billion or so. So 4 billion needs 10 digits in base 10, right? Because it's 4 followed by 9 digits. So 10 digits in base 10 requires 32 digits in base 2. So you go like, oh, that's a lot of zeros and ones to write, takes up a lot of space. You're absolutely right about that. And that's why we need to convert things into base 16. Okay? Well, but doesn't that involve a lot of calculations? Because don't we have to do a base 2 to base 10 and then from base 10 to base 16? Nope. It's a very easy straight shot. Okay? The only thing you have to remember is a table. 0, 0, 0, 0 in base 2 is 0 in base 16. 0, 0, 0, 1 in base 2 is 1 in base 16. Okay, you can probably work this out for the most part. Then 0, 1, 1, 1 is 7, 0. Oops, 1, 0, 0, 0 is 8. 1, 0, 0, 1 is 9. 1, 0, 1, 0 is 10. But in base 16, we don't want to write it as 1, 0, because if we're using base 16, a single digit can represent from 0 to 15. So we borrow letters from the alphabet. We say it's A, 1011 is B, 1100 is C, 1101 is D, and 1110 is E, and then 1111, which is the most you can represent using base 2, is F. This is base 2, this is base 16 or hexadecimal. It's just another way to refer to the same thing. Okay. Have you seen like strings of numbers, that has 0 to 9 and then A to F, in chunks?
ASCII.
The ASCII table, sometimes people use base 16, yep. When you want to enter a special symbol using Unicode, you're typing in a hexadecimal number, okay? Other times, when you flip over the base of a router, okay, of anything that you need to hook up, wirelessly, even, I was just recently using setting up my Ecobee, which is a thermostat system, the wireless, sensor, its own ID, and guess what? It is expressed in hexadecimal. IP address, IPv6, is in hexadecimal, okay? So now we still have the question, okay? I'm going to answer that last question before we transition to the lab. Is if you are given a long string of zeros and ones and you say, I don't want to write all the zeros and ones, it takes up too much space, what do? Well, it's easy. You group these things into chunks of 4 bits, chunks of 4 binary digits, okay? And then you look up a table. That's all you do. 1001, if you look up the table, is 9. 1010 is A. 0111 is 7. 0101 is 5. 0110 is a 6. And then 1011 is a B. So B, 6, 5, 7, A, 9 is the hexadecimal representation of all those zeros and ones. Is that process easy? Well, not initially, okay? Because initially you probably still have to look up the table a few times. But if you have done this for, let's say, 2 or 3 months, okay? And you do it like, just a few times a day, you would have memorized this table. Then you can just look at a long string of zeros and ones and quickly convert it into the hexadecimal representation, or the other way around. You can start with the hexadecimal representation and convert it back into the binary representation. There's no multiplication involved, there's no division involved, it's just table lookup. So yes, so we can start with base 2 to explain the concepts of addition, subtraction, and circuitry and stuff like that. But when it is time to express values that are kind of big and too much to represent using base 2 or too impractical in base 2, then we can switch to base 16. And that is why hexadecimal has a place in computer programming or to the computer industry in general, because it is so useful. Because the conversion is easy. Are we good so far? Yep. Mm-hmm. All right, no problem. So we'll get back to this later. Okay, so if you don't quite get the concept of base conversion from 16 to 2 or the other way around, it's okay. Okay, we'll get back to this later on. So for now, the lab is already done. I've already released the lab for today. So we'll go over to the lab and do this lab, at the and then your reading assignment for Wednesday is to try to finish the module on binary addition. So we are already into some portion of it, but there's a lot more that we need to go over. So I'll see you guys over at the lab, and now we can turn on the recorder. Thank you.